All right, this chapter we're going to talk about stoichiometry, which is the study of quantities of materials consumed and produced in chemical reactions. And chemical reactions are incredibly important. They occur every day as we transform food to energy in our bodies or make fertilizer by the Haber process, the production of ammonia, or the production of petroleum, and even in our body, the transformation of bacteria to insulin. So first off, this word stoichiometry, this first part, stoich, comes from the German word for amount. And it's the study of these quantities of materials consumed and produced in chemical reactions that we have to be concerned about. And we talked a little bit about the mole last unit, but that's the most common way in which we measure amount in chemical reaction. But first, in order to do that, we have to weigh a certain object, and you cannot get the mole just by weighing an object. So that's where we get the average atomic mass on our periodic table. We get many of those atoms, and we get the average mass of those atoms, and we use that as the mass of every single atom. So we count atoms the same exact way, even though, let's say, the average mass of hydrogen is 1. Maybe some hydrogen atoms have a mass of 1, some have one of 0.95, some have a mass of 1.05, but normally they average out to a mass of exactly 1. So we use 1 as the mass of every single hydrogen atom. So, as an example here, let's say we have a pile of marbles that weigh 394.80 grams, and 10 marbles weigh 37.60 grams. And you want to know how many marbles are in the pile. So first off, we want to know what is the average mass of one marble. So what we do, we take that number, 37.60, divide by 10 marbles, and we get an average mass of one marble of 3.76 grams. So 3.76 grams is the average mass of one marble. Now, every marble doesn't necessarily have that exact same mass. Maybe none of them have the mass of 3.76, but some have a mass of like 3.78 or 3.74 or 3.77, and so on. But the average between all of those averages out to 3.76. So now that we have the mass of one marble, now that we have the overall mass, we can take our overall mass, 394.80 grams, divide by the mass of one marble, and that is equivalent to 105 marbles. So this is extremely similar to what you will do in your lab tomorrow, and this is how we get the average atomic mass of those naturally occurring elements that you find on your periodic table. So the most common element is carbon, and this is the element that all other masses are based on. So the reason for this is that carbon-12 is exactly 12 what we call atomic mass units, or AMU. So AMU is the abbreviation for atomic mass units. And pretty much any element you see on the periodic table occurs as a mixture of isotopes. And remember, isotopes are those elements that have the same number of protons, so they are the same element, yet a different number of neutrons, so a different mass number. So here we have the three different isotopes of carbon, carbon-12, carbon-13, and carbon-14. And this one, the carbon-14, since its percentage is less than 0.01%, we're going to say that's negligible. So we are going to ignore it when we use our calculation for calculating the atomic mass, the average atomic mass of carbon. And you can only calculate the average atomic mass by using these percentages. And the reason why we're given these percentages, you just don't take an average of carbon-12 and carbon-13. You would only do that if there was an exact ratio or percentages of 50% to 50%. Obviously, that is not the case here. So here we have to convert each of these percentages to decimals. So 98.89% divided by 100, we get 0.9889. And here the actual atomic mass of carbon-12, we said it's exactly 12. So for this one, it's exactly 12.00 AMU. So here we multiply the decimal, the percentage of that isotope, multiply by the actual atomic mass. We get 11.87 AMU, the correct number of sig figs. Then we do the same thing for the other isotope, carbon-13. We convert 1.11% to its decimal form, so 0.0111. And then you'll always be given the actual atomic mass of carbon-13 is not exactly 13. That's only the case for carbon-12. So this atomic mass is actually 13.0034 AMU. So you multiply those two together, and you get a mass contribution of that isotope of 0.144 AMU. And now, to get the actual average atomic mass, we add those together. And with the correct number of sig figs, we get 12.01 AMU. And if you'll notice that 12.01 right here is the number for carbon on the periodic table. Okay, so you could, as long as you had these values for every element, the percentages and the average atomic mass of each one, you'd be able to calculate that mass that is present, that average atomic mass that is present on the periodic table. So the main point I want to emphasize is that even though a naturally occurring carbon atom doesn't necessarily have a mass of exactly 12.01, we treat each one like it does. So we assume, instead of just assuming there's different carbon-12 and carbon-13, we assume every carbon has an exact mass of 12.01. So this allows us to do all these sorts of calculations, these stoichiometric calculations where we're converting masses to masses and masses to moles. And so normally, either on the periodic table, it'll either be referred to as average atomic mass, or sometimes you'll just see it as atomic mass. And realize it's an average. Pretty much every atomic mass is not a whole number. It's a decimal. So that all those different percentages, it's an average of the two. That's why it's not a whole number, like mass number, which is just protons plus neutrons. And a mass spectrometer is a very common chemical and biochemical piece of instrumentation that's used to separate mixtures of elements and compounds together to get their relative abundances. So for example, here, this is the relative abundance of neon atoms. So that's how we get that average atomic mass of neon of 20.18. So the majority, and that makes sense, the majority of neon atoms, above 90%, have a mass of 20. Now, we calculated the average atomic mass of carbon. We knew it was carbon. It was a known element. But here, this is an unknown element. We want to calculate the average atomic mass and then identify the element from our periodic table. So we use this same process. We convert the percentage to a decimal. So 62.60 becomes 0.6260. We multiply that by its mass in atomic mass units. So times 186.956. We make sure here our answer will have 4 sig figs, and the units here are AMU, or atomic mass units. So the mass contribution of this one, 117.0 AMU. We do the same thing for the next isotope, 37.40. And one point I want to make here, I don't necessarily, or in the problem, you wouldn't necessarily be given this value. If there's two isotopes and you're given the percentage of one, automatically you should be able to derive the other one, because always the percentages will add up to 100%. So even if you weren't given this 37.40, you should realize, okay, 100% minus 62.6% is in fact 37.4%. So be aware of that in a problem. You might not necessarily be given the percentage if there are just two isotopes. Or if there's three isotopes, you could be given 2 out of the 3 percentages and have to derive the other percentage. So we multiply that percentage by its atomic mass, 184.953, and we get the mass contribution of that isotope with the correct number of sig figs, so 69.17 AMU. Now that we have each mass contribution, now we can add them together, and with the correct excuse me. So now with the correct number of sig figs, so we'd get 186.17 AMU. However, we can only have one digit to the right of the decimal point. So our final answer here, 186.2 AMU. So that's the answer for our atomic mass. And now we look at our periodic table. What element has an atomic mass of 186.2, or one that's very close to 186.2? So we find that that is rhenium, or the chemical symbol Re. Okay, and now next class, we're going to talk about moles, how we convert from grams to moles, and how moles are a measure of amount, because that's what we use to count atoms in chemistry. I'll see you next time.